is 0 over h?
0.
That's right, 0 over h. Since h is always non-zero, right? It approaches 0, but it's never going to be 0. This fraction is always the number 0. So now you have the limit of 0 as h approaches 0 is certainly 0.
Wait.
And it's revealed to us the slope of this function for all time. Yep. Say that?
Okay, so explain the first two steps again.
These two?
Yeah.
Okay. So this is
What is this?
definition
Yeah.
of slope of curve. That's our derivative, right? Okay. That's the formula for it. The function we're talking about right now is a constant function. Maybe it's 2 or 5 or something, right? Constant function we're calling c right now. So we can take care of every case. So f of x plus h is c. No matter what you put into the function, it's always c.
Why wouldn't it be c plus h?
Because it's always c. Because it's not varying. It's not like it's f of x equals x, and you put in something for x. There's nothing you can put into. You know what I mean? It's c. It's like 5.
Okay.
There's nowhere to even put in an expression.
Okay.
It's always 5. So c minus c, because that's what this is going to be as well. This is also c.
Yeah.
Is 0. 0 over h. Remember that h is approaching 0, but it is never going to be 0.
Okay.
So 0 over non-zero is already a 0. And now this is a constant. So the limit as h goes to 0 for a constant is that constant. So that is our constant slope.
Okay.
Always find the slope of the constant, not the slope of the actual function. Right? I mean, slope.
We did the same thing in this context.
Yeah, we always find the slope of the tangent, not the slope of the actual one.
They're the same thing.
It's yeah, it's the same thing, but I'm just.
Correct. Yep. Next case. F of x equals mx plus b. Standard non-horizontal line. Non-horizontal line. Okay. What's the answer for the slope of this curve? Is that? Not 1 necessarily. M. M. F prime of x, the slope of the curve is always m. For sure. Because, again, its slope is constant, right? And it is that value, that's what it stands for in slope-intercept form. Slope-intercept is m. Let's quickly prove it like we did the other one. Limit as h approaches 0 of f of x plus h. I think there's a reason. I want you guys to remember this formula. One thing. You need to memorize this formula. F of x plus h. Well, if it's mx plus b, it's our non-horizontal line, that's going to be m x plus h minus b, or plus b, minus f of x. F of x is mx plus b. H, take the limit as h goes to 0. So if you expand this out, we anticipate there should be a factor of h living above, and there is. You will have mx minus mx, so that part goes to 0. mh has no counterpart. Now you have b minus b. So the only thing left above is an mh. So lim of mh over h as h approaches 0 is the same as the limit of m as h approaches 0, which is just m. Again, a constant slope, but it's not necessarily 0, right? It's the slope of the original line. Slope of original line. Whew. Next, that takes care of all linear functions. Now we need to go to quadratics. F of x equals x squared. Who knows the answer? I want the derivative. What's that?
Drop the power by 1, multiply the coefficient.
I think it's like 42 or something. All right. So Snyder say what's the solution?
Drop.
Go ahead.
Drop the power by 1 and then multiply that by the coefficient.
Multiply what by the coefficient? The new power or the old power?
New power. No, old power?
Old power.
Yeah.
Okay. So what Snyder's referring to is what's called the power rule. Power rule. So what you do is you simply make the original power a coefficient, and you drop the power by 1. So 2x is the answer to this case. Right? 2x. We can easily prove it using the definition if we had to, but since Snyder has cut to the chase on this one, we'll allow it. Yeah.
Can you explain that again?
There is no explanation. That is just a fact. I didn't show why that's the case.
No, like something you said confused.
Oh, sorry. All you do is take down the original power to a coefficient, it becomes coefficient, and you drop the power by 1. And that is the derivative, all right? You guys okay with that?
Wait, can you do another one with like, that's not squared? Can you do one with?
We do all sorts of them.
Okay.
Let's say it's the cubic function, x cubed. I'm going to use the power rule again. I'm going to bring down the 3. I'm going to lower the power by 1 to a 2. So f prime, the derivative, that is the slope, is going to be 3x squared. Okay. That's how you take derivatives of powers. Power function, not exponential function, it's power function. So then if we extrapolate to f of x equals x to any power, and the power rule should yield that f prime is in x to the n minus first power, right? That's the power rule right there. That is the power rule. Now again, I've let this go without any proof whatsoever. That is those are the facts on the ground. So that last one is one you want to keep in mind, and the rule you wish to apply anytime you want to find the derivative of a power, right? Okay. Another important rule. That only gives us those little guys. But not every function you have is just something squared or something cubed. They sometimes have more complicated things associated with them. So let's say, for instance, your function was slightly more complicated. So we have the constant multiple rule. So the function is c times a function. Okay? Not just a function. You've multiplied the function by a number. Okay? So you want to take the derivative of this thing. So it's going to be c f prime of x. You can take the derivative of the function itself and then multiply by the constant afterwards. Okay? You don't have to incorporate the constant into the derivative process until after the fact. So for example, let's say we had f of x, I'll use different letters since that's f, g of x is 5x squared. Back when we had the power rule, all we knew what to do with was x squared. Now it's 5x squared, it's got a number on the front. So what are you going to do? I'll ignore the 5 for a second, just ignore it. Take the derivative of x squared. What do you get? Okay, so apparently I can take the 5, which is the constant on the front, and multiply it by the derivative of the variable part. And then I get 10x, which is hopefully what you expected anyway. Okay? Make sense? So it doesn't just work for powers. This is any function, by the way. The few we have right now are powers, but this works for any function. Constant multiple rule. I would like to start introducing some ulterior notation for these things now, and that is the dy dx notation, or df dx. So df dx is the same as f prime x. These two things mean the same thing, right? But sometimes the d dx notation has an advantage when writing out these types of things. So the way I'll explain it now is this. So again, let's see at 5x squared. What I want to do is I want to take d dx, d